Okay guys, so if we are in the family of three periodics in the elliptic billiard, these blue triangles, so they're interscribed in a pair of confocal ellipses, consider the family of their circumcircles, these red circles centered on C1 or the circumcenter X3, and alongside with a family of bevan circles. The bevan circles shown here green, centered on C2, they're actually the circumcircles to the excentral family, shown orange here. Okay, so I have three periodics, their circumcircles, these red circles, and their bevan circles, these green circles, i.e. the circumcircles to the excentral triangles, these orange triangles. So we have this nice family. Okay, all right. Now neither radius, not shown here, is constant. Actually, they are shown here, right? You can see here that neither radius is constant. All right, very good. Okay, now I want to bring a new concept, or actually a classic concept in planar geometry, that of limiting points, right? So given a pair of circles, for example, this red one and this green one, but any pair, they can be nested, non-nested, there is a pair of points known as the limiting points between two circles. I'm going to leave some information in the description. So they're known as limiting points. Now these 2 points are such that if you perform an inversion of the pair with respect to either one of the limiting points, you get a beautiful result. You get a new pair of concentric circles. So let's go ahead and draw the limiting points. But before I draw the limiting points, I'm going to make this confocal pair here, this elliptic billiard pair, be a little more eccentric so that we can view the limiting points a bit better. So it's the same situation here. So I just made my my elliptic billiard be a bit more eccentric. We still have 2 circles, right? We still have the red. Let's play with the scale. We still have the circumcircle red and the bevan circle green. Now let's consider this pair of circles, and now let's draw their limiting points. So here are the limiting points, LA and LB. Now the magic here is that if I were to invert the pair, the red-green pair, with respect to either LA or LB, I would get this new pair of inverted circles. Now let's change the inversion radius a little bit so we can appreciate a little better what's going on here. Okay, so this first pair here, this first aquamarine blue pair here, is a concentric pair centered on CA prime. Okay, so this pair here. What is this? This is actually the inversion of the red-green pair with respect to the first limiting point, LA. Now you can see here a second pair of aquamarine circles centered on CB prime, and they are the result of the inversion of red and green with respect to the second limiting point. So I can actually draw a line between 1, 2, 3, 4, 5, 6 points, because these guys are all going to be collinear. Okay, and you can see here that LA and LB are the limiting points of the red and green pair. That is to say, these are points with respect to which, if I inverted the original pair, so you can imagine that there's a circle centered on LA, say unit radius one, and a circle centered on LB, another unit radius one. If I inverted the original pair with respect to either one of these 2 circles centered on LA and LB, I get 2 brand new pairs of concentric circles. So here's the first pair centered on CA prime, and here's the second pair centered on CB prime. Of course, if I change the inversion radius, okay, I can change the position of these pairs, but they remain concentric, and I can just alter a little bit for visibility what these pairs look like. Okay, and they're concentric pairs. Now there's a beautiful property of inversion of a pair of circles with respect to the 2 limiting points, and that is that the radius of the outer concentric to the inner concentric on either pair is the same. So if I divided the radius of this circle by the radius of this circle, I would get 1.605555. Then if I go to the second concentric pair, and if I divide the outer radius by the inner radius, I get the same number. Okay, so this is a property of this limiting point algebra. Okay, and it's pretty cool. Okay, so you can see here that if I change the inversion radius, okay, I can change the size of these pairs of concentric circles, but the ratio of their radii does not change. The position of their centers also changes because it's related to the size of this inversion radius. Okay, very good. But what this video is about is invariants that you get in the family, the Poncelet family, inscribed, the three periodics, right, inscribed in the confocal pair, the elliptic billiard family, regarding its limiting points. First of all, if I iterate this family, so if I traverse this family, you can see here that you're going to get an interesting first invariant. Very first invariant you get is that the ratio of radii of the two concentric pairs is invariant. So you can see here that they're stuck at 1.6055. Okay, so this is a first invariant. A second invariant, okay, or property, is that let's look at the locus of these two limiting points, okay, as you traverse the family. It's a true gem that the locus of these limiting points of the pair circumcircle and bevan circle are both circles. We don't understand this yet, we haven't proven this yet, but you can see here that LA and LB each are moving along a concentric circle. So here's the circle of LB. Let's watch this more closely as the family iterates. So you can see that LB, one of the limiting points, is moving along that circle. Let's look at the other. Let's look at the other circle, the other locus, which is this one here, LA. So the locus of LA is also its own circle. So this is pretty beautiful result. Now, if I actually were to do the same simulation on that other confocal pair that was less eccentric, I get something that is a bit harder to visualize because one of the loci is pretty close to the origin. You see, you get this circle that is pretty close to the origin. It's a pretty small radius, and the other circle is all the way out there, okay, outside. But we still get the same property. Now notice that the ratio of concentric radii has changed. Let's switch back to that other family. It used to be 1.6055, but in this last concentric confocal pair, it changes, but it's also constant. Okay. Now notice that if I were to list the four concentric radii, 1, 2, so this is from the first pair, the ratio of 0.14 by 0.07 gives me that. And here's the radii of the second pair. I also get this ratio. The four concentric radii are all varying, be it on this less eccentric family, be it on the more eccentric family. So you can see that the four concentric radii are varying. However, the ratio is invariant, and both limiting points are moving along circles. Okay, so this is the first property that I wanted to show here. Let's go to a second property. Let's look now at a family that has a, I'm going to forget about the eccentric circle, the eccentric family, so let's go ahead and turn this off. Okay, and I want to look at a family. Okay, so first of all, let's investigate this family, what it looks like. Let's scale this up. Okay, so this is the same family. It's still the confocal family, but now I'm gonna pick out two different circles. Okay, before I had the circumcircle and the bevan circle. Now I simply want to take the incircle of this family. So let's turn off the locus so we can simplify this. Let's turn off the endpoints and the limit points, so we can just focus on the two circles. So now I'm going to focus on the pair comprising the incircle of this family and its circumcircle. Okay, what happens to the limiting points? So let's go ahead and draw them. Now again, you can see that they're moving out there. Maybe these are more visible. I don't need to go eccentric. Let's look at their loci. So now for this particular pair, incircle and circumcircle, you don't get a lot of harmony, but you get some harmony because these two loci are perfect ellipses. You can see here that I'm indicating the axes of the ellipse of the first limiting point. So let's call this LA. And here's the ellipse, the axis of the ellipse of the second limiting point, LB. You can see that the ratios, the ratio of axes, their aspect ratios are those numbers. Okay, these are loci. But it is a sufficiently interesting and rare phenomenon that we've picked out two circles two pretty well-known circles, the incircle and the circumcircle, and their limiting points move along ellipses. Let's look at the inverted circles, and to do that, so that we can get a better picture, I'm going to increase the eccentricity of this pair. I'm still looking at incircle and circumcircle, but I'm going to now do a more eccentric pair, more eccentric confocal pair, and I'm going to look at the limiting points and their locus. Yeah, so now they're more visible. Whenever you go a little more eccentric, these limiting points, they tend to get closer to the center, and it's easier for us to visualize them. So you can see that there are two nice ellipses here. Okay, C1 here is actually the circumcenter, C2 is the incenter, now X1. Now let's look at the line connecting these guys. Okay, this might be indicating that I have something pretty far out, and I don't know what that is. Oh yeah, so probably the centers. Okay, so if I do this, I can bring these guys in. Yes, I see what that means. So yeah, so if I actually were to draw the pairs, right? The pairs of concentric circles that are getting out, that are a result of the inversion of the incircle and the circumcircle with respect to either limiting point, I can watch that pair, that first concentric pair, centered on CA prime, and I can watch the second concentric pair centered on CB prime. Now notice that the ratio of outer to inner radius is 1.6055. Okay, now we've seen this number before, and this is the curious fact, right? Here am I measuring the ratio of radii of the inverted incircle and circumcircle with respect to either limiting point, and I'm getting 1.6055. Now if I go back to what we had before, let's go back to the previous family, which was circumcircle and bevan circle, that ratio is also 1.6055. So this is rather curious, right? The limiting points are different, right? So if I'm on this family, I'm getting this LB over here. If I go to the family we just were looking at, I'm getting different limiting points, but yet post inversion, the ratio of outer to inner circle in these two concentric pairs is the same. So it seems like this ratio for the pair circumcircle and bevan and the pair incircle and circumcircle is the same. Okay, even though in the first case the locus of my limiting points were circles, as we saw before, and now the locus of these limiting points are two ellipses. Yet that ratio of concentric radii is the same, meaning that there's a new result here. Okay, so I have these three results now: the circular locus on the pair circumcircle with bevan, second result elliptic loci for the limiting points of the incircle and circumcircle pair, and the fact that the ratio of radii for the two cases is the same. So that's the third statement. Okay, now let's go to a third and final family here. Third and final family, the family of incircle. So this is sort of the Poncelet family with incircle, right? Here's a Poncelet family with incircle. So it has an outer ellipse and a concentric inner circle. All right. Now let's look at what's happening in terms of limiting points here. What are the limiting points doing? Perhaps I'm going to take the eccentric pair, which is going to be, well, I don't know if this one is going to be more friendly or less friendly, but let's draw the loci of the limiting points. I think they're both circles as well. Yes, I can see here that the loci are circles. I just have to see the locus of the outer one by changing the scale, obviously. So it's going to be out here somewhere. Yeah, there it is. And let's see which one is more visible. Yeah, they're both bad, but we can make it out. So yeah, so I have this Poncelet pair with an outer ellipse and an inner circle, concentric, and we're getting the same result. The loci of either limiting point of the pair circumcircle with bevan is a circle. Okay, so it's similar to what we had in the confocal pair. So this is another case where we get the circular locus of limiting points. Let's draw the the eccentric triangle, so that we recall that, just for reference, I'm talking about again the circumcircle and the bevan circle, the circumcircle of the eccentrals, and I'm finding here that on this Poncelet pair, the loci of either limiting point is also a circle. Of course, I can show the two pairs of inverted circles. Let's see if I can make them out. I recall one of them being pretty small. Yeah, the other one is really small, and it's over here. But if we change this inversion radius, we can see it better. So yes, you can see that there's that pair there, and there's this other pair over here. But if you notice that their ratio is also conserved, the fact that these ratios are equal is just a fact. It's a more general a property of inversion with respect to limiting points. But the fact that they are conserved seems to be a property of perhaps concentric Poncelet. This could be true for perhaps any concentric Poncelet, but we've seen it so far that it is true that these ratios are conserved either for the incircle pair or the confocal pair. It remains to be experimented with other families to see if these ratios are preserved, even though the loci of the limiting points might not be circles or ellipses. Okay, so there you have it for 4 or 5 phenomena, depending on how you want to call it. 3 of them related to the loci of these limiting points. They are circles for the confocal when you're dealing with circumcircle and bevan, and also for the pair with incircle. And they're ellipses when you are in the pair, in the confocal pair, but you are actually considering the incircle and the circumcircle. And then you have this other phenomenon whereby the ratio of incircle, circumcircle, inverted concentric circles is the same if you're considering either incircle with circumcircle or circumcircle with bevan circle. Okay, so 4 or 5 results out here that I'm going to list in the description. I hope you've enjoyed this video, and I'll see you in the next one. Thank you very much.